This is a short slideshow on projectile motion, which I've prepared mostly using the references listed on the first slide here. Over time, the ideas of projectile motion have changed. Initially, the ideas of Aristotle were predominant, and Aristotle believed that most projectiles moved in a horizontal direction, followed by a fairly quick vertical drop before they returned to Earth. Over here on this left-hand side of the page, you'll see there is a tab which you can click on. It gives us a definition of ballistic trajectory, which, as you can see, is the path of an object through the air. Of course, there are rules, and it must be subject only to gravity and air resistance and no other forces. So the trajectory that an object, in this case something which is ballistic, takes through the air is called its ballistic trajectory. Luckily for us, Galileo came along and did a large number of experiments on projectile motion, and through his experiments, which included things like dropping objects off the Leaning Tower of Pisa, rolling marbles down slopes, as we did in physics preliminary, he discovered that vertical motion and horizontal motion are actually independent of each other. And when you add them together, you will get the parabolic shape made by a projectile. The horizontal motion is constant velocity, does not have any acceleration, so the the velocity that the projectile has at the start is the same horizontal velocity that it has at the end. The vertical motion, however, is accelerating, and the acceleration is due to gravity. When we put both of these vertical and horizontal motion together, we get projectile motion, which is the shape of a parabola. But just keep in mind that the vertical motion and the horizontal motion are independent of each other. The motion of an object as viewed by you depends on the frame of reference. So if you are at a distance to a projectile moving, then you will see the projectile moving in the shape of a parabola. If, however, you launch the projectile and run at the same speed as the projectile, you will actually only see the vertical component of motion, because the horizontal component of motion is non-existent because of the frame of reference that you are in, where you are travelling at the same speed as the projectile. You will remember from preliminary physics that the motion of a moving object relative to another moving object can be calculated using the formula on the screen at the moment. So the velocity of object B can be calculated by subtracting the velocity of object A from the velocity of object B. I have an example over here on this tab. Car A is travelling at 100 kilometres per hour, and car B is travelling at 80 kilometres per hour in the same direction. The question is, what is the velocity of car A compared to car B? Now, this question actually is the opposite of the equation that's underneath it on the screen. What we have to do is subtract the velocity of car B from the velocity of car A in order to determine the relative motion of car A. So if we do that in our head, we should get 100 kilometres per hour minus 80 kilometres per hour to get the answer, which is underneath the green tab down here, of 20 kilometres per hour. This formula also has another name in HSC physics, which is called the Galilean transformation. There are some rules as to describe an ideal parabolic trajectory, and here they are. Air resistance must be negligible, so that the object is not slowed down due to air resistance. The height and range of the motion has to be small enough that the curvature of the Earth can be ignored. If we think about the frame of reference, and we might use, say, a piece of graph paper, we would look at the vertical component of the motion as being the y-axis, and we know that the vertical component of the projectile's motion is subject to the force of gravity, so acceleration due to gravity, and you'll see that the subscript y is used next to the letter A to indicate that acceleration in the y-axis is due to gravity. we usually represent the up direction as being positive and the down direction as being negative, which means that acceleration due to gravity in a problem is represented by minus 9.8 meters per second squared. The horizontal component is usually represented along the x-axis of a graph, and we look at the horizontal motion as being positive if it is going to the right, negative if it is going to the left, and we know that acceleration is zero. We have constant velocity, so you'll see that the acceleration in the x component, so the x direction, is zero as represented on the screen. There are, of course, some properties of ideal parabolic trajectories. Once we get to the maximum height of a parabola, the velocity in the y direction is equal to zero. So effectively the object is stationary at the top of the shape. The trajectory is horizontally symmetrical about the maximum height. So there will be the same amount along the x-axis on the left and the right-hand side of the middle of the trajectory, the parabolic trajectory. It takes the same time to reach the maximum height as it then does to fall back to the original height that the projectile was emitted from. Our initial speed is the same as our final speed as long as we are on horizontal ground, and our maximum height can be reached if we have our launch angle at maximum at 90 degrees, and we will get our maximum range if our launch angle is at 45 degrees. Anything in between this changes the height and the range. We also need to know that all objects projected horizontally from the same height have the same time of flight as one which is dropped at rest from the same height. So what that tells us is if we drop a marble from the height of the desk and we roll a marble off the side of the desk and they are released at the same time, their time to reach the ground, so their time of flight, would be the same. So that is because they're both affected by gravity and both start with initial velocity of zero in the y component, in the y-axis. They will, however, land at different places on the ground because they have different horizontal velocities. And lastly, but not leastly, we need to be able to solve problems of projectile motion, and we need to go back and look at some of our SUVAT equations that we had in preliminary physics. Now you might remember that S stands for displacement, and sometimes in some of our formulas R is also used to represent displacement. Displacement along our x-axis is represented by delta x, which is our final location, so our final x position, take away our initial x position. Our displacement in the y component, or the y-axis, is represented by delta y, and we of course can calculate that by our final y minus our initial y, which could be zero. We will have to know our SOHCAHTOA trigonometric equations. We will have to know our SOHCAHTOA trigonometry equations, and we also need to know some other equations which are on our physics formula sheet. The ones which I've highlighted in yellow are on the physics formula sheet, so you will not need to remember those, but you will need to know how to apply them. Our standard formula here, velocity equals displacement over time, or speed equals distance over time. I think we all know that one. We can rearrange that to get our average velocity is our change in displacement divided by our change in time. That's on your physics formula sheet, so you don't have to remember it, and you can rearrange it to get other formulas. We also had as one of our SUVAT equations that our average acceleration is our final velocity, subtract our initial velocity divided by the time taken to change our velocity. And that's the standard formula for acceleration. These are our SUVAT equations, which are to do with straight line motion. So the other three SUVAT equations which we would be familiar with are listed down here in the table. The ones in yellow are on the physics formula sheet, so you do not have to remember them. The other ones can actually be derived from other formulas, or if you are not very good at rearranging formulas, then you will have to remember them and understand how to apply them. If we look at the horizontal component of projectile motion, we will see that we have four formulas down here listed in the table. Again, the ones in yellow are listed on the physics formula sheet, so you don't have to remember them, but you will need to be able to derive them if you need to use the other formulas not highlighted in yellow. And formulas used to solve the vertical component of projectile motion are listed down here in the table, and the ones in yellow are on the physics formula sheet, and these two formulas which are not highlighted in yellow you'll either have to remember or be able to derive from your other formulas. If you go across the table, you will notice that the formulas relate to each other. So our straight line motion SUVAT formula, which is on our formula sheet, V equals U plus AT, we would know that we have no acceleration in our horizontal component, so that means that the AT part is 0 and our formula becomes Vx equals Ux. If we use that formula in the Y component, so the vertical component of, if we use that formula in the Y component or the vertical component of the projectile motion problem, we will have a look at vertical velocity is equal to vertical velocity is equal to our initial vertical velocity plus our acceleration times our time. It's effectively the same formula which is on your physics formula sheet, but only for the vertical component of projectile motion. I hope this has helped you get started in solving projectile motion problems.